Welcome to our lecture series, Extreme Architecture. Within our module, Emerging Fields in Architecture. I'm glad to welcome our guest, Georgi Petrov, today. He has been lecturing within our module already multiple times, but today's talk is a very special one, and I'm looking forward to it. Georgi Petrov is a practicing architect, structural engineer, and space architect. He is Senior Associate Principal at the New York office of Skidmore, Owings Merrill, SOM, where he usually works on high-rises, long-span, and specialty structures around the world. But today, you will hear a lot about construction, form finding, and optimization of buildings, but not with or maybe with some examples from Earth, from the portfolio of SOM, but also with an example from a lunar construction site. As a space architect, Georgi has over 20 years of experience in both designing and advocacy for the field. He is the current chair of the AIAA Space Architecture Technical Committee, and he is also teaching at the New York University and at the MIT. Welcome again, Georgi, to our lecture series. We're welcoming you very much.
Thank you very much for the lovely introduction. And yeah, I'm very happy to follow in Sandra's footsteps as the chair, following her of the Space Architecture Technical Committee. And thank you for having me so I could share some thoughts with you today. Can you share my screen? We good? Okay, thank you. So I'd like to always start my talks with this image. And I know you probably can't answer back, but I hope everybody here knows what this image is. This is the picture of Earth taken from Voyager as it was flying out of the solar system looking back. And everything you know is here is this one little pixel that we have. And it's the only planet we have right now, although if you're here in this class, you're probably interested in expanding our species to other planets. But so far, we're here, and there's sort of a lot of us. Depending on what kind of projections you look at, in the next 25 years, there'll be 1 to 3 more billion people, which is good news for you, because as architects and engineers, there'll be a lot of work, because we're going to have to build places to live and places to work and places to play for another 3 billion people maybe. But the challenge is that we can't keep building the way we do, the way we've been building, especially in the West, with the tremendous amount of embodied carbon that goes into the structures that we create. And so how do we create more efficient and more sustainable structures? And that also relates both on Earth, but also it's very apt for how we build in space, where, right, mass and reducing quantities is one of the key drivers for any design for space. And at SOM, we kind of approach this through a merger of architecture and engineering. These are the 3 guys that are long dead, Skidmore, Owings, and Merrill. And there's 2 of them are architects. Skidmore, Owings, and Merrill was an engineer. So from the very foundation of the firm, we've been doing this collaboration with architecture, engineering, working together from the very very first step. And then, to this day, we're always a joint team of architecture, engineering. We have big major offices around the US, in London, in the Middle East, and in Hong Kong and Shanghai. We actually have a new office in Melbourne as well, if anybody's from Australia here. And we do many different types of buildings, cultural, institutional, super tall. Because we are this big collaborative of many architects and engineers, we don't really have one particular style or one thing we do. We have a very varied portfolio. But we're kind of very known for our super tall buildings. So Burj Khalifa, the world's tallest structure, is ours, both architecture and engineering. And this used to be more red, but a number of the world's tallest buildings are ours in both architecture and engineering. And the first part of this optimization story I'd like to tell you is the invention of the modern skyscraper. We'll get to space eventually, but that a lot it has to do with this person whose name is Fazlur Khan. He's a structural engineer from Bangladesh that worked in our Chicago office. And after World War II, in the 60s and 70s, he really was instrumental in developing how we build skyscrapers to this day. Just a little background, tall buildings are mostly governed by lateral loads, not gravity. I mean, they obviously have to support against gravity, but mainly wind and some places seismic loads. And so you can think of a tall building as a cantilever sticking out of the ground. So, a typical cantilever goes out and there's no end support. And if you rotate it 90 degrees, a tall building is basically a big cantilever that's being pushed by lateral loads. And, to design an efficient structure, you kind of think of it as a beam, right? You have the building and you kind of imagine it as a big beam where you want to put the material as far away from the center as possible. Just like we have, wide flanges that we build structure with, right? The point here is that by putting all the material to the perimeter, you get the most efficient structure. Well, before World War II, most of these early skyscrapers, this heroic age of classical skyscrapers, were actually not built like this. They were a sort of a uniformly distributed forest of columns. Basically all moment connected, kind of like the same structural system you would do for a 2 or 3 story building, but just extruded right up. And so what Fazlur Khan here, working with one of the architects from the Chicago office, Bruce Graham, kind of realized that, the modern skyscraper would really want to be as efficient as possible. And so the best thing to do is put all the material in the perimeter, but, a solid big tube is basically a chimney. It's not a very good place to be in. And so, their first attempts at this was how do we add windows and mullions and make it a livable building, but put all the structure on the perimeter. And so, throughout experimenting, we have this diagram of appropriate structural systems for tall buildings for various heights. And SOM has done the first iterations of these for most of these systems. But we're going to start over here. And their first attempt were these 2 buildings in the 1960s. And actually a third one right after that. So these are the first 3 iterations of them. And what you see here, every vertical you see is a column, is a structural column, and every horizontal is a structural beam. And so these 3 buildings basically create this tube by putting all the material on the perimeter. So this is like the first level of optimization, taking the material where it's not doing much from the middle and putting it on the perimeter. And then another iteration is really the John Hancock building, which is kind of realization that you could put all the material on the perimeter, but if you tie all of the columns with these X braces, you could have a lot further apart spaced columns that are not so close together. Not every mullion between every window needs to be a structural column. And so this is just a disclaimer, my favorite SOM building. It's a beautiful story of integration where the client came to the SOM with wanting an office building and a residential building. And Fazlur Khan said, we'll put it both on top of each other and we'll build it for the same amount of material. You get twice as tall building. You get the building tapers because, right, residential residences want to have small lease span. Everybody wants to have a room with a window. Offices, you could have, a bigger lease span. The mirror could be wider. And so, putting the residential on top means that even the lowest residential apartment is already halfway up the building and you get much better views. The building also tapers because the wind loads increase as they go up. And so this is more efficient structurally and it's more efficient architecturally, and both of them work together very well. And so this is the building under construction. You see all of the structures on the perimeter. One key thing that's very important in our work and in trying to optimize structures is that you could come up with a very, very efficient geometry, but usually the most efficient geometries create more complicated connections. And so in order to capture all of the savings and all of the efficiency in your optimized geometry, you have to always be thinking about connections and how things are put together. And so in this case, for example, they rotated the diagonal members so that you could have as small connections as possible, because you could connect both the top and the inner and the outer flange and things like that, making the connections as tiny as possible, leaving as much for sunlight to come into the building. And they were really worried at the beginning that, we've never put these crazy diagonals. Nobody's done this before on the perimeter of a building. And in fact, these days, the apartments that have the diagonals through them are kind of more sought after and sell for more than the apartments that don't have diagonals. But the really important part in this story is that, I could kind of tell through this graph. This is a graph of the number of stories as you go up in a building, and the average amount of material, in this case steel, per built area. So, you have some minimum amount for the floor framing, right? And you add more floors, but they're all the same, right? The floor framing between the columns stays the same. Then you have the columns, and as you add more stories, the columns actually do have to increase. And so you're kind of adding a little bit more material because you have bigger and bigger columns. But then the building, remember, is a vertical cantilever, so it has to resist the wind loads. And you need to add much more material to resist the wind loads. So Fazar Khan called this the premium for height. Typical building would go like this. And so by optimizing the structure, John Hancock is really right down here. Almost all of the structure that's put in to keep the building up is also working to resist the wind load. And so you have almost nothing as the premium for height. So it's like the most efficient tall building you can imagine. So you should always strive to be, down here. So this is the first step of SOM, even back in the 60s, going higher and doing heroic structures, but using the least amount of material. And so, we can think of this optimization in several ways. If you have, let's say this is a tall building, an example, you have a design domain. You can put material anywhere in a certain area or volume in this case. So the first thing is topology. How are the elements connected? After you find the correct topology, the next step would be to find the correct geometry. And so trying to optimize the geometry is the next key step. And then if you're a really good engineer, the very last step is actually sizing the members correctly. And if you want to really take seriously this idea that you want to design structures that has the minimum amount of material, that's the minimum amount of embodied carbon, really all of the savings are in the first two steps. The sizing is really almost an afterthought. If you have the right topology and the right geometry, then the structure would be, the most efficient. The last step is just following the code and filling out. I think this is where we are very strong, because we as engineers and architects together can design the geometry of the building. It's not like our architects draw some blobby thing in Rhino, yank on it, and then give it to the engineer, say, make this work. If that's the design process, then you basically skip these two first steps and you go directly to sizing. And then obviously you can make almost anything stand up these days, but is it really the right way to think about designing structures and be the most efficient? So in the last 20 years, we've kind of built up on this. And it was kind of by discovering this old paper from an engineer from Australia called Mitchell. And he wrote a really short paper, basically starting with Maxwell. And Maxwell is the Scottish engineer that's famous for describing light in physics, but he also had some great additions or thoughts on engineering. And by using, starting with some ideas from Maxwell, he derived these most efficient structures. So this is basically a two loads on either side of a support, and this would be the most efficient truss. And then the one that we use a lot is the idea, if you have a force here and you have a support here and you have unlimited domain space, you can put material anywhere you want. The most efficient truss to support a cantilever is actually this shape. And we also have a lot of tools to take this idea and make it usable. So how do we make this practical? Because if you use the basic principles, there's only very few actual solutions you can compute by hand. And so at SOM, we write a lot of our own code, taking these ideas and making them useful. And so this is one example where this is one tool where you have the design domain, you fill it with a very dense grid of elements, and then you slowly run iterations, taking away elements that are not contributing to the stiffness of the structure and keeping only the ones that do. This is another tool which does very similar thing, where again, you start with a domain and you apply the loads, you apply the restraints, and you run iterations of it, again, taking material where it's not being efficient and reinforcing areas where the material is helping the most to support your loads. And you keep coming up with these same patterns that Maxwell discovered by hand 100 years ago. And if you take this and apply it to the skyscraper, right, you have the domain of a regular building, and you apply the lateral loads, you can play around with the density of it, but you start to get these patterns that are emerging. And then this is Fazlur Khan analyzing the building many in the 1960s, but with more computational power these days, we can actually improve on the John Hancock. So this was the original John Hancock with the X braces. They're all straight members. But actually, you kind of want to have more curving, gently curving members rather than the straight X braces. So this would be the next iteration. And we've actually built a couple of these. So this is a building in Sydney, Australia, which is a much shorter building. But it turns out that a more efficient shape for the bracing is if you take the middle point and move it up to about 2/3 of the bay. So we call it the high-waisted brace. We have another version of it here in Chicago, in the US. Again, we have not quite built a super tall with it, but we have two built examples with this much more efficient shape. You can do the same stuff for bridges. So if you have a bridge and you have the two supports and a bunch of loads, and you run the same type of optimization again, you get these patterns emerging. Obviously, you can't take this and say manufacture it. And so you have to always kind of have a step of rationalization of whatever these tools are given to you. And so this is would be kind of the most efficient shape for a simple span truss. And if you take it the absolute, most optimized but unbuildable, by rationalizing it a little bit, you can actually get pretty close to it in the amount of material, which is a lot more optimal than the typical standard truss that we're used to in Pratt truss in this case. And so we have a built example of this. I got to design one. This is for a hospital in Atlanta. This was an existing building. This is the new building we were designing, and we needed a pedestrian bridge to connect the two sections of the hospital. And it had to be a two-level bridge, one for patients and one for the public that's out open. And so we kind of took this same approach of form finding rather than just doing the typical truss. This is the new building, and the existing building is behind us. So we took the design space, right? This is where the two levels are. We applied the loads and the supports, and we ran our optimization. And then obviously then, simplified it. It was pretty cool to see this built. They actually had closed the road only for one weekend, prefabricated the big pieces, and lifted it over a couple of days. And you can see this crazy looking truss, but it's quite a little more efficient than the typical structure. You always have to have some constructability elements. For example, the bottom had to actually slope, so it's not as simple as the diagram. But again, we had to think about the connections. How do you make these non-straight elements? We ended up with solid steel nodes that are then welded to the HSS sections. This is them getting fabricated. This is the pieces being lifted. And I got to visit it when it was still under construction. And here's the finished bridge. This is the top level with the truss. The bottom level just hangs from it. And this is it being in use these days. So this is the first example of this optimized truss that we have is a bridge, besides the two tall buildings. Other ways to optimize is, again, starting with the geometry. So this is a stadium and a tennis center that we designed for Kuwait University about 15 years ago. This was a university with a track and field and soccer stadium, football. And we had these 200-meter long arches, kind of inspired by the motions of athletics and birds in flight. And the original geometry that our architects came up with was this sort of circular arch, but we pointed out to them that the catenary shape is a lot more efficient. This is an old idea from Robert Hooke, as hangs the flexible line, but inverted stands the rigid arch. This is made famous by Gaudi. If you've ever seen any of Gaudi's work, he didn't have any computational tools, so he actually built models with cables and hung little bags of sand to derive the form finding. A lot of stuff in Barcelona when you go see it. But for our purposes, if you take the circular arch and then you take a catenary, just by changing the geometry very slightly, you get a giant reduction in the forces that the arch has to support. One thing is that this is, because this is a roof that was curving in plan, the load is not just the self-weight of the arch, but the load kind of varies because you get more tributary area towards the middle. And so, we did this little animation to show, you take a circular arch, you do just a normal catenary under the self-weight, and then a catenary that's optimized for the actual load. And then you invert them and you hang the actual load, and then you see that how much you could reduce the forces you have to design for by tweaking the geometry just a little bit. This is kind of, again, the two catenaries. You can't almost tell them apart. And again, a very similar theme. We had this very optimized arch, but then we had to spend a lot of attention to how to make the connection at the bottom. And that each arch was made out of these three pipes that formed a sort of a triangular truss. And we made it tapered towards the end. And, you can draw your idealized geometry coming to a point, but then you have to actually make a connection. And so we kind of actually ran the arches past each other so that we have the pipes would be spaced out, and then we could design an abutment to come and meet it. And so we spend a lot of time thinking about how this is built and how it's put together and all the elements to transfer the load of the steel truss to the foundations. And this is it to scale. This is one of my partners at the SOM and the architect. You can see the arches coming in. And, you can see how light it is. It's 200 meters span, but it's super airy and very, very, very thin. There's very similar other stadiums of similar size with much more massive trusses that were, not optimized for geometry. On a smaller scale, we did this on a skylight. This is at the Air Force Academy, the university for the Air Force in the U.S. And it's out in Colorado at the foothills of the Rockies. And the original campus was built by SOM in the 1960s, including this is the chapel, which kind of inspired by the jets. It's kind of a classic SOM early modernist project. And we got to add the skylight in the same campus. And so it was a kind of a classroom and a mock trial area. It's called a Center for Leadership. But the North Star, it's kind of a symbol for the Air Force, a guiding principle, both for navigation and for, its steadiness, pointing the right way to truth, and other metaphors like this. And so the idea was to point this north, exactly towards the North Star. We studied a bunch of ways to do it. And then this is the form we came up with. And so we took this geometry and we wanted to minimize the size of the mullions to make it as transparent as possible. So if you make the same size members, it will deflect a lot. But if you take the deflected shape and make the members deeper where it's needed the most, and you run the same load, then you get this optimized structure that deflects a lot less. And if it deflects a lot less, you could have a lot more transparent, much smaller gaps between the glasses. The glass units could have a much smaller connection, and so you get a lot more light coming in. And this is it. This is the what you see here is the structure, is also the mullions that are supported the glass, and it's also the shading, so that it light comes in, but it's not the direct light hitting the bottom. There's this art piece in the middle. You can kind of ignore that. But again, marrying the architecture and the structure to create the most efficient shape. And so with these sort of terrestrial examples, now we'll move a little bit of how we've applied this to our work in space. And the first project that we did was a collaboration with Lockheed Martin over a couple of years to do a design for a lunar module. And this was a rigid module, not an inflatable. The next project I'll show you is an inflatable. And this is kind of how they would aggregate together to start forming a lunar base. But the little bit that I want to show you here is that whenever you're sending something into space, you have to think about the loads, right? And so everything has really two load scenarios. There's the part where it sits in the rocket and gets launched. And depending on the rocket, it could experience, 3 to 5, maybe more Gs. So very big acceleration or, gravity load that's pulling down. When you're launching, most of these habitats that we're thinking of sending out for more permanent settlement probably won't have the humans in it. So you don't have to have it pressurized, or you don't have to have it fully pressurized. And so the main load is actually a gravity, quote unquote, or acceleration. And if you remember from your physics, they're the same thing, gravity and acceleration. But then when you get it to the destination and you put it down, you have a very different loading condition. You have on the moon, right, 1/6 G, so very low gravity. Actually, gravity becomes almost negligible, but you're trying to pressurize it. And containing 1 atmosphere of pressure is actually about 10 times more force than the gravity force we see on Earth. So the floor you're sitting on in your house or whatever you guys, wherever you are, is usually designed for 2 to 4 kPa live load. Containing 1 atmosphere is I think 10 kPa of live load, so an order of magnitude bigger. And so you have to design for these 2 different configurations. And most of the pressure vessels that have gone out, this is, I think, the Orion, have this regular grid of reinforcing around the pressure vessel. And so we're thinking of, well, is there a better way to optimize this? And so we took this same approach where we applied the load in a software that, again, looks at where the material is being efficiently used and takes away part of the material where it's not. And you come up with these optimized patterns for where to put the reinforcement around doors and windows and things like that. If it's just a solid pressure vessel without any doors or windows, then the pattern is pretty straightforward. But once you start introducing openings, then you start to get these interesting patterns that are more efficient than the straight regular circumferential and radial positioning. But the project I want to spend the most time talking to you about is our design for the Moonvillage that we did in collaboration with ESA from 2018 to 2022, and we're still kind of working on it a little bit on the SOM side. But the idea, right, for the Moonvillage, hopefully this would be not news to you, was Jan Werner's, Director General of ESA's idea is to take the approach of the International Space Station and apply it to how we go to the moon, right? And the International Space Station, you have many different partners coming together to share the same infrastructure. So, you know, the ESA's module, for example, doesn't have to have its own solar power, it doesn't have to have its own heat rejection, it doesn't have to have its own propulsion. It could, you know, partake in the general infrastructure that's already there. And so, you know, the idea of the Moonvillage is to take this approach to going back to the moon, where we share infrastructure and many different people can plug into it rather than competing, everybody bringing everything themselves and duplicating and triplicating effort. And so, you know, ESA kind of tasked us with what could that actually look like. And we worked on 3 different scales. We worked on the master planning, we worked on the individual habitat, and then we actually looked at a lot of the actual subsets or systems of the first habitat. I'll kind of skip over this. There's another recording of the series where I go in depth on the master plan, but the punchline is that we propose this linear growth model where we have a band of the actual habitats, and then next to it a band of infrastructure that's all of the external elements that are needed to support research and ISRU and the habitats, and then another band of activities where it could be set aside for each of the different participants in the Moonvillage. So if you have a government agency that wants to set up a long-term trek to explore a certain part of the moon, they could use this as a staging ground. Next to them, there could be a tourist outfit where it would be doing outside lunar sports and people experiencing the different gravity and so on and so forth. And then on this is the actual ridge of the Shackleton crater on the South Pole. The crater is on this side, and then the sort of relatively more flat terrain is on the left. And, you know, we had this idea of adding some poetry to it and leaving a part of the moon undisturbed as a pristine lunar park. Because if you've seen, you know, when humans go everywhere, they drive and they make a big mess of it. So we wanted to leave a bit of the moon undisturbed. And we decided to place it on this one particular end, because if you know, on the South Pole, because of the tidal lock between the Earth and the moon, the Earth always appears kind of generally in the same place on the horizon. This is an animation. This is our site right here, right? This is Shackleton crater. Our site is right here, and you're looking towards the Earth. And throughout the year, the Earth kind of moves, but it's always generally in the same direction on the horizon. And so we had this idea of like, well, let's place the pristine lunar park in the direction of the Earth. And so you have this image of you're always living on the moon, in your habitat, looking at the edge of the rim, and the Earth is always there, beautifully reminding you of home. You know, and then the single habitat, we designed what would be the first one. And so by definition, you don't have any others. So all of the functions need to be put into the first one. So this one had a workshop, a lab, the crew quarters, and an experimental garden on it. The idea is that as you get more and more of these arriving, you would start specializing them. Just like on Earth, we have different buildings having different functions. Maybe one would be entirely a lab, another one would be entirely for crew quarters and creation, another one for storage, and so on and so forth. But we decided to concentrate on this particular one, and so this would be the lower floor. That's the workshop. This would be the crew quarters going up and up. I won't get into the detail of this, but related to form finding, I want to tell you another story. And so after publishing the main design a couple of times, we got invited to it used to be the 2020, but because of COVID, it became the 2021 Venice Biennale. And the theme was, how will we live together? And so it was perfect to fit for us because, living on the moon or designing for space is always about living together in a confined space. And so we proposed to build a art version of our full module that could be experienced from the inside. Not a technical model, but sort of an artistic one because it is the Venice Biennale. And we're going to have it 3 floors. And on the ground level is where we would be able to experience it. You wouldn't be able to go up because we have to think about it in terms of a large amount of visitors coming and going and things like that. And so in order to use this opportunity and to show this idea that, when you're going to the moon, you have to use the least amount of material and form finding, we decided to really concentrate on this first level floor and really optimize what would be the most efficient structure. And we had several sort of patterns thinking about. And, these days, a lot of work is done on 3D printing. Back when I started thinking about space architecture 20-some years ago, 3D printing was in its infancy. And so my early work was more about robotic construction. But in the last 20 years, additive manufacturing has really matured quite a bit to where we can, have a lot of thinking about it. The NASA has had several 3D printing challenges in relation to how you might use it in outer space. And so we were thinking, well, we'd like to use it with metal. And if you think about welding, is depositing a little bit of molten metal. And if you put a welding arm on a robot that's controlled by computer, you can 3D print. And we partnered with MX3D. They're a steel metal 3D printing company out of the Amsterdam. Oops. That's a link. Never mind. Sorry, just a second. Let me stop that. And they're famous for the steel bridge that they built a few years ago. I'm sure a lot of you have seen it. It got a lot of publicity. This is its first mock-up, and then it actually got installed in Amsterdam, and this is their queen opening it and things like that. And they've done a lot of other work on connections for timber elements and the robot arms, optimized robot arms and bicycles and things like that. So we teamed up with them to create this. And fortunately, they had already done a lot of research on the material. It is an unusual material, right? 3D printed steel. And it has different properties, whether you're measuring the strength along the path of the deposition or across it. And so they had taken coupons in 3 directions and trying to determine the properties of the material in both, along or across the deposition. They've also kind of built little sample columns to test the compressive capacity of it, crushing different circular or square shapes we could use the material research they had already done. This was, now at this point already 5 years ago. So if you look at the literature, there's a lot more that's been done. It's a really hot topic that a lot of people are thinking about. But we approached it the same way. This was the design domain, the shape of the floor. We wanted the big opening in the middle, and then we had, 3 pairs of supports. And so if you run our same optimization, you get this crazy pattern. And again, same thing. You can use this as inspiration, but you can't really take this and say, computer, build me one. So we took several steps of trying to rationalize this geometry. And this was our first attempt at it. You might notice eventually this is not what we ended up with, but this was part of the learning. What we wanted to do is have these glass panels sitting on top of it. Again, you wouldn't make a floor out of glass if you're sending this to the moon, but for the Biennale, this was our design challenge. And, when you're having glass in public areas, either people walking on it or above it, it has to be multiple layers that are laminated together for safety. And so this was our typical detail where the glass would sit on top of a little flange, and then this would be the optimized structure below. And so we took the limits of the technology, right? When you're dropping molten material, steel, you can't just drop it in empty space. And so with 3D printing of steel, you could print about 30 degrees or so off of vertical and still have it work. And so we took this idea and said, okay, well, we'll print it upside down. We'll have our little surface where the glass sits on, and then we'll print these conical shapes of varying depth. And, that would be our efficient structure. This is kind of the original sketch of this. And then this was our first stab at it. The problem, though, is that when materials get heated or cooled a lot, they change dimensions. And when you have the big variation of temperature between molten metal and room temperature, they change a lot. And so we had this problem where we would start depositing, and just by the material cooling, it would start bending. It would start bending so much that it would deviate from the actual geometry, and you couldn't keep printing because the computer had no idea that in the meantime, its substrate had changed. It still had the digital model, which was all perfect. And so we tried all sorts of different things, like even this really thick piece of metal, by depositing the 3D printed material, it bent it. You can see how much force there is in this cooling of metal. So we were like, okay, this is not working out. So we kind of looked back at what MX3D had done before and how they had 3D printed their bridge. And so they had actually printed it the long way, the other way. And so we took that idea and rethought of it completely. So we would be printing not up, but across. And that way, the area that needed to cool was a lot smaller. And then we also had to think through of the reach of the robots. So each robot has a sphere of how it would go. So we broke it up into 2 pieces. And then we would had a element around it on which the glass could sit. So we simplified it quite a bit. We did more studies to make sure that we're the thinnest possible material. This was what it would have looked like. And then this was some tests. We still had to do a lot of little tweaking of the geometry around the transitions from one branch to another. And in the end, they 3D printed it. And it still exists somewhere in Amsterdam. Unfortunately, we couldn't build the rest of the pavilion because of COVID. Our general contractor got pulled out at the last minute. But we did have the structure already. So I think I'm at time, and I like to leave some time for questions. So I will end my story there for today. Thank you.
Thank you, Georgi. We have a lot of questions and you have little time. So
Okay.
let's rush through your questions.
The first one is in German, so you have to translate it for me.
No, it's just that some people want to go on the Zoom.
Okay.
But the first questions I put in from our YouTube chat, I think it's very short. Have you calculated the lighting in the project?
Which project? The space ones?
No. The one before the skyscraper,
The skylight.
the skylight, yes.
Yeah. We have a whole team. They used to be called now they're called Sustainability Engineering System. They used to be called High Performance Design Group. That do a lot of this analysis. So they have a lot of the tools for lighting, for glare, for heat transfer. So they do very sophisticated modeling of each of our projects from an energy point of view. And so we always work with them together as well. So yes, the answer is yes on that one.
Thank you, Georgi. The next question is from Olivia Choikits. Olivia, do you want to ask a question yourself?
Yes, I can. So my question was, how can space architecture improve the operational efficiency of lunar missions, particularly in terms of resource management? So I guess I'm looking at which design innovations could enhance the efficiency of resource management.
What do you mean by resource management? Like the energy and or the materials that are used on it, like the operational?
Mostly the operational, yes, the materials and the operational part.
I mean, I think the big challenge in space is moving material around, right? That is why it's so difficult and hard, partly is because it's very hard and expensive to move molecules in and out of gravity fields. And so the more you could use the resources available at the location, the better you would be. You don't have to bring everything from Earth. And so I think we're far away from being able to build our own habitats on the moon or Mars, because I think this problem of containing the pressure is really hard. But the reason of going to the moon or Mars or the South Pole is that there's material available there that we could use, in much more so than in open space where you only have energy, you don't really have material. So architecturally, I think anything you could build there is a big step towards making an efficient operations. It's anything you don't have to bring from Earth. And what does that mean? On the South Pole of the moon, you mostly have oxygen, hydrogen, hopefully a lot of water, maybe some other organics, and so from that you could make water to drink and oxygen to breathe and maybe oxygen and hydrogen for fuel. But if you have maybe a little bit of carbon also mixed in, you have oxygen, hydrogen, and carbon, you can make a lot of plastics, right? And so I can imagine making a lot of the furniture and a lot of elements for repairing things out of locally derived plastics. Eventually, if you want to grow plants in a meaningful way, you need nitrogen. So you have to bring the nitrogen from Earth, because there likely isn't any, unless there's some ammonia mixed into the stuff on the South Pole. We really don't know. So the way architecture can come up with help is trying to come up with cool ways to use the local resources, so you don't have to keep bringing everything from Earth. I don't know, is that kind of what you were getting at in the question?
Yes, I think it covers it. Thank you.
Okay, no problem.
Before we go to the next question, I have to refer to the previous lecture, because it's the design for a very sufficient toilet. Nitrogen is a resource that we bring with us.
Oh, from the humans.
You may consider that.
Yes.
Okay, Emeka, do you want Or would you like to
Yeah.
ask a question, please?
Yeah, I can try to simplify it. I think just what softwares do you guys tend to use? Have you noticed that there's any that are better suited for any specific tasks? And then specifically to the actual designs, or there's any things that you learned that you didn't expect throughout the process of actually working on these like optimized structural designs?
Yeah. So that's a big struggle, is to find the right software, because there's a big variety available out there. And the last 10 years, the generation of ideas usually has been done in Rhino. It's kind of in Grasshopper, for scripting. And there's a variety of tools available, both online, and we write a lot of our own stuff. For this software for optimizing and putting the material, there's a company called Altair, and makes this product called Hypermesh that does a very good job of it. The two little tools that I showed you several times of, those were written in-house by us, SOM. So we're always kind of trying to stay at the leading edge of of what is the best tool, and how do you transfer the data back and forth. So usually it's some kind of a Rhino and Grasshopper to come up with the geometry and collaborate between the architecture and engineering. Then for the analysis, we use ETABS and S-Frame and Strand, are 3 finite element programs. And then usually documentation is all done with Revit at the end. But Revit is just to like make the sheets and the plans and stuff like that. Otherwise, you kind of start when you do a lot of these optimizations and material optimizations and form finding, you kind of start to learn that usually the shortest load path is the best. You imagine where your force is that you're trying to resist and where you're trying to get it. And the least convoluted path is usually the most efficient one, using the least amount of material. And then another one is that nature kind of wants to bend forces gently. You want to, that's what you see, all these curved patterns that go from the load to the support. It's kind of a pattern that emerges a lot. I don't know the underlying mathematics for it, but get the load to where you want it to go in the shortest amount of path, and then if you have to, curve it gently.
That's really helpful. Thank you so much.
Cheers.
Thank you, Georgi. Do you have time for one more question?
Let's do one more.
Okay, Atira, please.
So I have got 2 questions, but I'll ask the first one. How do you envision the Moonvillage evolving over time, and how does the initial design accommodate future growth and adaptability?
Very good. Well, as I mentioned, there's a whole other recording with Sandra about that one. But in short, we tried explored different master planning ideas of how humans have formed new settlements on Earth. And I think at the beginning, at least, this linear growth really makes the most sense for the rugged terrain of an unknown planet. And then I think, the big part of why we're going there is to learn how to live there. So we'd pretty soon test our different ideas and come up with new ways to make habitats and modules. But I think it's very important that the first ones are, contributed by architects and engineers, and by architects, because it's a new level of living on the moon, right? We've been there for short missions, and everything that's gone so far has been kind of designed by engineers, and the humans are the last thing that goes in there. What we can bring as architects is that we start thinking about the humans and what they're doing and trying to wrap the technology around that, instead of trying to force the human into some kind of a technological solution. So well-designed habitats, but probably they'll change pretty quickly as we find out what works and what doesn't. But this idea of a linear master plan growing in one or two directions for at least for a little bit. I think after a certain size, the linear master plan becomes inefficient, right? Because everybody's trying to get through to the same place. And then hopefully by then we would have figured out a better way to do it. But at the beginning, at least, I think the growth, this linear growth along the ridge of the Shackleton crater is a good solution, at least the one that I thought of. Thank you.
Thank you very much, Georgi. Thank you for your time. And thanks for this interesting and surprising talk today again.
Thank you.
I enjoyed it.
Excellent. You can, if there's more questions, I'd be happy to answer them by email to the students.
Wonderful. So we will collect them. Thank you very much.
Thank you. Good night, everybody.